This is episode 3, Magic of Prime under Mathematics Universe. In our previous 2 episodes, we started with checking prime numbers. In episode 1, we were checking from 2 to n-1. In episode 2, we were checking between 2 to n divided by 2. And now in this episode, I say it is enough to check between 2 to square root of n. Why is it enough to check between only 2 to square root of n? There should be some reason, right? And let's look into that reason by taking an example. The example is, we'll take n is equal to 100. And what is the region that we are trying to check? It's between 2 to square root of number. So first, let me take square root of 100, which is 10. Now, let us pick all the factors of 100 less than 10, which is typically less than square root of n. So what are all the factor for 100 less than 10? Let's start with 1. Let us list out all the factors. Then we will come to understanding why is it enough to check only between 2 to square root of n. And the first factor is 1. The next factor is 2, then followed by 4, and then followed by 5. 1, 2, 4, 5. These are the 4 factors of 100 less than 10. Why are we doing all these things? We will understand now. Let's do step number 1. We will pick n 100 and we will divide it by 1. What is 100 divided by 1 is? 100 divided by 1 is 100. The quotient is 100. And that 100 is a factor of 100. Next, we will take the same 100 and we will divide it by 2, the second factor. 100 divided by 2, what we will get? We will get 50, which is also a factor of 100. Again, 100 divided by 4, 25, which is also a factor. Then, 100 divided by 5, quotient is 20, which is also a factor of 100. And now you see here, 20, 25, 50 and 100. These are the only 4 factors of 100 greater than 10. There are no other factor for 100 greater than 10. So which means what we can infer from this, what we can understand from this. For every factor on the left side, which is for every factor less than square root of n, there exists another factor which is greater than square root of n. 100 divided by 100. 1 and 100 connected. They are pair. Let us take them as a pair. Then 2 and 50 is a pair. 4 and 25 is a pair and 5 and 20 is a pair. So every factor actually exists as a pair. That is the first observation that we have. So which means 1 and 100 are pairs, then 2 and 50 is a pair, then 4 and 25 is a pair, and 5 and 20 is a pair. And mathematically we can make a statement. And what is a statement? If you take a number n and when the number is divisible by I, that is, when you take a number n and when you climb I is a factor of n. When you climb I to be the factor of n, you can also climb that n divided by I also will be a factor. That's, for example, if you say 5 is a factor for 100, then you can also say that 100 divided by 5, 20 is also a factor. So every factor exists as a pair. Let me repeat. When you take any number n and you say I is a factor, then you can also climb n divided by I also to be a factor. So basically I comma n divided by I is a pair that we are speaking about generally. Where when we take I and n divided by I as a pair, then I is going to be occurring less than square root of n and n divided by I will be greater than square root of n. That's point. And with this point, we can also add one more inference, observation, which is if for every factor on the left side there exists a factor on the right side, can we also say that if on the left side we have 4 factors, right side also we will have 4 factors, because all the factors are pairs. If on the left side we have 4 factors, right side also there is going to be 4 factor. If on the left side there is going to be 3, right side is also 3. Left side, if there is 2 factor, right side is also 2 factor. Left side, if we say there is going to be 1 factor, right side also there is going to be 1 factor. If we say left side we have 0 factor, right side also we will have 0 factor, which means that suppose if we prove that there is no factor between 2 to square root of n, can we also say mathematically that there will be no factor after square root of n? So if there exists a minimum of 1 factor inside square root of n, there will be 1 factor after square root of n also. So what is prime? Prime means from 2 to n minus 1, there should be no factor. So what I say is that between 2 and square root of n, if there is no factor, after square root of n also there will be no factor. So no need of checking after square root of n and wasting up to n divided by 2. Let's not go up to n divided by 2. Let's stop up to square root of n. So the important point is how many factors we have from 2 to square root of n. The same number of factor we will have after square root of n also. So between 2 to square root of n, if there is 0 factor, even after square root of n also, we will have 0 factor. One more point to add. What is going to be the condition that we are going to write in the implementation? Let us discuss that beforehand. In the 2 previous episodes, the conditions that we wrote were I less than or equal to num minus 1 and I less than or equal to num divided by 2. Now here the condition should have been I less than or equal to square root of num, whereas square root is going to be an inbuilt function that is available to us via math library. But I'm going to tell you a very different way of writing this condition, much better way of writing this. So where I will take the same condition a bit mathematically, I less than or equal to square root of num, and now squaring on both sides, both LHS as well as RHS. So let's square on both sides. On the left side we have I square, which is I multiplied by I, and then it's going to be less than or equal to square root of num. If you square it, square root and square is going to be cancelled out. So it cancels each other and it becomes just simply num. So instead of writing this condition, mathematically we can also write this condition, both are same. But what is the purpose of changing that? Why can't we stick to I less than or equal to square root of num? And this inbuilt function, when it is called, it has a lot of background logic which will take more time. But coming to this condition, multiplication takes 1 unit of time and less than or equal to takes 1 unit of time. Simple, just 2 unit of time. So in terms of time, this way of writing the condition is better than this way of writing the condition. Hope the concept is clear, and let's jump into the implementation. Coming to the implementation, again it's a very simple change here. Initially it was like I less than or equal to num minus 1, which we changed to I less than or equal to num divided by 2, and now the condition should be changed into I multiplied by I less than or equal to num. And we also saw why we are writing this condition. And that's the only change that we are going to do in terms of implementation. Just I multiplied by I less than or equal to num. What that condition is doing, it is just checking whether the value of I is less than or equal to square root of num, which is what we need exactly. So now after this, we will now again go ahead with compiling this. So there is no syntactical error. Compilation works absolutely fine. Now we'll execute it. and let's say input be 1, which is not a prime, then we'll go with 2, which is a prime, then 3, which is a prime again, 4 is not a prime, 5 is a prime, then 6 is not a prime, 7 is a prime, 8 is not a prime, 9 is not a prime, 10 is not a prime, 11 is a prime, then 12 is not a prime, then 13 is a prime, and it goes on and works absolutely fine. But this is not the utmost efficient way. Yes, it is efficient, but not the utmost efficient one. There is still one more approach which is much better than this, which we will explore in the next episode.